100 degrees. That is not a temperature forecast. That is the difference, right now, this weekend, between one end of America and the other. Phoenix approaching triple digits while Wisconsin sits at wind chills near zero. Same country, same sky, same storm. And here is the part that should genuinely unsettle you. This isn't two separate weather systems doing two separate things. This is one storm, a single spinning low-pressure engine, simultaneously burying the Midwest in up to 40 inches of snow, launching a tornado outbreak from Texas to the Atlantic coast, and doing absolutely nothing to cool down the Southwest. One storm, 3 disasters, one weekend. Stay with me until the end, because the warning buried inside this forecast is the part nobody is talking about. Subscribe and follow along, because this storm is not the end of the story. The same atmosphere that is loading 100-degree temperature split across one country this weekend will keep loading. The jet stream does not rest. And when the next setup starts building on the models, the next kitchen sink pattern, the next overnight tornado window, this channel breaks it down in plain language before the noise takes over. You are going to want to be here for that. Now let's get into it. Something is coming this weekend that shouldn't be meteorologically possible, and yet every forecast model agrees it's happening. A single storm system. One low-pressure center spinning over the continental United States. And it is simultaneously about to bury the upper Midwest in up to 40 inches of snow. Unleash a tornado outbreak stretching from Texas all the way to the East Coast, and do absolutely nothing to stop the Southwest from baking under temperatures approaching 100 degrees Fahrenheit. Before spring has even officially started. All at the same time. All from the same storm. Let that settle for a second. Right now, as you're watching this, meteorologists across the country are staring at their models with the specific kind of focus that means they are genuinely alarmed. This isn't a news cycle exaggeration. This isn't clickbait weather drama. The numbers are real, the threat is real, and over 100 million Americans are sitting inside. This thing's reached this weekend. So let's talk about what's actually happening, because this storm deserves more than a scrolling alert on your phone. The northern side of this system is going to do something almost violent. The Upper Peninsula of Michigan is looking at somewhere between 20 and 40 inches of snow. Northern Wisconsin could see 20 to 30 inches. Minneapolis is staring down 10 to 18 inches. These aren't estimates with wide error bars. These are the high confidence ranges coming out of the National Weather Service, and the models have been consistent for days. Wind gusts on the snow side of this storm are expected to reach 50 to 60 miles per hour, which means whatever falls is also going to be moving horizontally. Visibility will drop to near zero. Roads will become traps. And emergency crews will be operating in the kind of conditions where response times are measured not in minutes, but in hours, if they can respond at all. Meanwhile, the southern flank of this exact same storm is a completely different story, and in some ways a more dangerous one. A tornado outbreak is expected to develop across a zone stretching from East Texas through Arkansas, Missouri, Illinois, Indiana, Kentucky, and into Tennessee. That's not a small threat corridor. That's a diagonal slash across the middle of the country. But here's what makes meteorologists particularly nervous about this event. The Storm Prediction Center has already issued a Day 4 enhanced risk for portions of the East Coast. A Day 4 enhanced risk. That means forecasters were confident enough about a tornado threat 4 days out to issue an elevated warning category for states that rarely see that kind of setup. Washington, D.C., Raleigh, Wilmington, parts of the Mid-Atlantic. That level of forecast that far in advance happens only a handful of times per decade. We're talking about 3 comparable events in the past 11 years. And while all of that is unfolding east of the Rockies, the western third of the country is operating in a completely different season. Phoenix, Las Vegas, Los Angeles. All of them are approaching 100 degrees Fahrenheit before March is over. Los Angeles hasn't officially broken its March heat record since 1879, a record that has stood for 147 years, and this weekend it might finally fall. Phoenix could see its earliest triple-digit day on record. The Southwest is sitting under a heat dome so strong that forecasters believe it could persist for 2 weeks. And over 200 daily temperature records may be broken across the country before this pattern finally relaxes. Now hold on, because here's the number that should stop you cold, so to speak. Phoenix will be near 100 degrees. Wisconsin wind chills will be at or below zero. That creates a temperature difference of over 100 degrees across the continental United States. At the same time, across the same country, under the same sky. That kind of atmospheric contrast doesn't just sound dramatic, it's physically significant. It's a measure of the energy available in the atmosphere, and that energy has to go somewhere. How does one storm system produce winter, spring, and summer simultaneously? To understand that, we have to follow this storm hour by hour, because the timing of what's coming is just as dangerous as the storm itself. Every major storm tells a story, and this one begins quietly, the way the worst ones always do. The system starts as a rapidly deepening mid-latitude cyclone forming over the plains. Saturday evening, the opening chapter. Snow begins across Montana, the Dakotas, and Minnesota. Snowfall rates start at 1 to 2 inches per hour, which is aggressive, but not unusual for a March system in that region. Most people in the affected areas go to bed Saturday night, thinking they know what kind of storm this is. A spring snowstorm. Cold, inconvenient, but manageable. They would be wrong. Overnight Saturday into Sunday, the surface low begins to deepen significantly. The central pressure of the storm is expected to fall toward 990 millibars, and if you know anything about how atmospheric pressure drives weather, you know that number matters. Lower pressure means stronger inflow. Stronger inflow means stronger contrasts. The storm is essentially becoming more organized, pulling harder at the atmosphere around it, dragging warm Gulf moisture north and Arctic air south like a spinning engine that keeps accelerating. By Sunday afternoon, that warm, moist air from the Gulf of Mexico is surging northward with real force, and severe thunderstorms begin developing across Texas and Arkansas. The warm sector of the storm, the region ahead of the cold front where unstable air is building, starts to wake up. Then, late Sunday afternoon, a squall line begins organizing along the advancing cold front. This is the mechanism. A long line of intense thunderstorms beginning to form and march northeast. By early Sunday evening, storms are intensifying across Missouri and Illinois. Around 8 or 9 p.m. Sunday, severe weather approaches the Chicago metro area. And this is where I need you to pay close attention, because what happens after dark is the part that doesn't make the morning news in time to warn you. Late Sunday evening, the squall line continues eastward, and wind shear increases with every hour. After midnight, the tornado threat spreads across Indiana, Kentucky, Tennessee, and the Ohio Valley. These aren't the big, slow-moving afternoon supercells that you see chased on television. These are nocturnal, embedded tornadoes, rolling through population centers while most people are asleep, and they are among the most dangerous weather events that exist on this planet. We'll come back to exactly why in a moment, because it's important enough to spend time on. Monday, the storm lifts toward the mid-Atlantic and East Coast, carrying that elevated tornado threat with it, which is why the Day 4 enhanced risk exists for that region. The system doesn't just pass and leave. It keeps evolving, keeps threatening, keeps escalating all the way to the Atlantic seaboard. The most dangerous part of this entire storm happens when most people are asleep, which means the warning you need to hear isn't just about the blizzard or the heat or even the tornadoes themselves. It's about timing. Because a tornado at 2 in the afternoon and a tornado at 2 in the morning are not the same event, even if they're identical on radar. Here's a fact that most people have never been told, and it might be the most important thing in this entire video. Nighttime tornadoes are approximately 2.5 times more deadly than tornadoes that occur during the day. Not slightly more dangerous. Not marginally elevated risk. 2.5 times more lethal. The research on this is consistent and sobering, and it comes down to a combination of factors that all converge at once when a tornado touches down after midnight. The first factor is the obvious one. People are sleeping. A daytime tornado gives you visual cues, a darkening sky, a rotating cloud base, the particular shade of green that people who've seen it will never forget. You can look out your window and process what you're seeing. At 2 in the morning, your first warning might be the sound of the thing itself, and by then you have seconds, not minutes. Outdoor warning sirens are designed to be heard outdoors, not inside a home with the windows closed and your phone on silent. If you are not monitoring weather alerts actively, the warning system can fail you entirely, not because the system isn't working, but because you are asleep. The second factor involves the specific kind of storms expected in this event, and this is where the meteorology gets genuinely chilling. Embedded within the squall line are what scientists call quasi-linear convective system tornadoes, or QLCS tornadoes. These are tornadoes that form inside long lines of thunderstorms, rather than from isolated rotating supercells. QLCS tornadoes form quickly, sometimes in under a minute. They last only minutes, sometimes just seconds. They are exceptionally difficult to identify on radar, even for trained meteorologists, because the rotation that produces them is tightly wrapped inside a chaotic storm structure that moves fast and changes constantly. There is almost no warning time. With a classic supercell tornado, meteorologists might have 20 to 30 minutes to issue a warning. With a QLCS tornado embedded in a fast-moving squall line at midnight, that window can shrink to under 5 minutes. The squall line feeding into this event is being driven by a low-level jet stream forecast to exceed 70 knots. That's roughly 80 miles per hour, at about 5,000 feet above the surface. This jet is functioning like a massive conveyor belt, transporting warm Gulf moisture, atmospheric instability, and rotational energy directly into the storm. Dew points ahead of the system are expected to reach the mid-60s in places, which for March is extraordinary. That moisture is fuel, and there is a tremendous amount of it. Cities that could be facing this threat in the middle of the night include Nashville, Louisville, Indianapolis, and Cincinnati. Damaging winds exceeding 75 miles per hour are possible even without tornadoes. The Storm Prediction Center has placed a 45% wind probability across parts of this region, meaning nearly a coin flip that you will see wind damage in those areas during the overnight hours. So if you are anywhere in the Ohio Valley, Tennessee, or Kentucky this Sunday night, charge your phone before you go to sleep. Turn your weather alerts fully on, and tell me why you wouldn't just do that right now. While tornado sirens may be sounding across the South overnight Sunday, the northern side of this exact same storm is doing something completely different, and somehow equally dangerous. The cold side of this system is where physics becomes almost theatrical. As the low-pressure center spins and deepens, it pulls Gulf moisture northward into a wall of air that is still firmly below freezing. When those two air masses collide, warm and saturated meeting Arctic cold, the result is snowfall on a scale that most of the upper Midwest experiences only a few times per decade. The atmospheric mechanics are almost elegant if you can step back far enough to admire them. The same energy source feeding the tornado threat in the south is simultaneously manufacturing the blizzard in the north. Two disasters, one engine. Snowfall rates in the most intense bands are expected to reach 3 inches per hour. 3 inches per hour. If that sounds abstract, consider that a 6-hour duration at peak rates would bury a vehicle. Roads don't become difficult in those conditions. They become impassable. And the snow is only part of the problem, because wind gusts of 50 to 60 miles per hour will take whatever falls and move it sideways, pack it into drifts, reduce visibility to essentially nothing, and make every road in the affected zone look identical. A flat white surface with no edges, no lanes, and no horizon. The forecast totals read like something from a particularly dramatic winter season. Upper Peninsula of Michigan, 20 to 40 inches. Northern Wisconsin, 20 to 30 inches. Minneapolis and surrounding areas, 10 to 18 inches. Milwaukee is looking at 8 to 10 inches. Winter storm warnings are already in effect across at least 16 states, and that number is expected to grow. Within parts of Minnesota and Wisconsin, there is also the possibility of light icing, a thin layer of freezing rain beneath the snow, which adds a particularly cruel dimension to travel conditions. Ice under snow is nearly undetectable until you're already sliding. Emergency response in these conditions becomes almost theoretical. A stranded motorist in a whiteout with 60-mile-per-hour winds and dropping temperatures is not in a situation that resolves quickly. And power outages from heavy wet snow loading onto trees and lines could leave entire communities without heat during one of the coldest stretches of the season. Here's a detail that captures how genuinely strange this storm is. Some communities that are currently watching thunderstorms and severe weather roll through could see snow on the ground within hours. Not the next day. Hours. The same system that delivers lightning and hail on its warm front will drop a foot of snow on its cold side, and the transition zone between those two worlds is moving through populated areas over the course of a single night. The strangest part of this entire storm, though, is happening thousands of miles away in the desert, and it has nothing to do with cold or tornadoes or snow. It has to do with heat so unusual that scientists are genuinely struggling to contextualize it. Let's go west, because the western third of this country is currently living in a completely different month than the rest of it. A historic heat event is unfolding across the Southwest at this exact moment, and the numbers are not subtle. Los Angeles is forecast to reach 95 to 98 degrees Fahrenheit. Phoenix and Las Vegas are approaching 100 degrees. These temperatures are running 20 to 30 degrees above normal for March, not a few degrees above average, not a mild anomaly, 20 to 30 degrees above normal. That is the kind of departure that climate scientists mark on charts with a different color than everything else around it. The Los Angeles March heat record is 99 degrees Fahrenheit, set in 1879. That record has survived every heat event, every El Niño, every warm pattern for 147 years. This weekend, it may finally fall. If temperatures reach 100 degrees in Los Angeles before the end of March, it would represent one of the earliest triple-digit readings in the city's recorded history. Phoenix is in a similar position, potentially logging its earliest 100-degree day ever documented. Across the country as a whole, over 200 daily temperature records may be broken before this pattern relaxes. 200 records in a single weekend. The mechanism driving this is a structure called a heat dome, and it works almost exactly like it sounds. A strong, high-pressure ridge builds in the upper atmosphere over the western United States, and it acts like a lid on a pot. Normally, air circulates, rises, cools, and releases heat. Under a heat dome, that circulation is suppressed. The air subsides, meaning it sinks, and as it sinks, it compresses and warms further. The heat stays trapped beneath the ridge, unable to escape, accumulating day after day. Forecasters believe this particular heat dome may persist for 2 weeks, which puts the Southwest in a prolonged stretch of pre-summer temperatures during what should still be late winter. And here's the thing about that heat dome that makes it more than just a weather story. On the other side of the country, Arctic air is being dragged southward behind the cold front. In some locations east of the Rockies, temperatures will drop 40 to 50 degrees within 24 hours of the storm's passage. The temperature difference between Phoenix near 100 degrees and Wisconsin wind chills near or below zero exceeds 100 degrees Fahrenheit across the continental United States. At the same time, under the same atmospheric system. That contrast isn't just an interesting number. That contrast is the energy source for the storm. The greater the temperature difference between air masses, the more energy is available to drive cyclone development, deepen pressure gradients, accelerate winds, and intensify convection. The heat dome and the blizzard aren't separate stories that happen to be occurring at the same time. They are feeding each other. The ridge creates the trough. The trough creates the storm. The storm creates the contrast. The contrast deepens the storm. To understand why that loop is so powerful right now, and why this particular storm is capable of doing what it's doing, we have to go 6 miles above the Earth's surface. Because the real engine of all of this is invisible from the ground. 6 miles above your head right now, a river of wind is moving at speeds that would exceed any commercial aircraft in level flight. It circles the planet continuously, rarely resting, occasionally speeding up to over 200 miles per hour, and it determines more about the weather you experience than almost any other single factor in the atmosphere. It's called the jet stream, and normally, loosely, by convention, it flows roughly west to east across North America in a path that keeps cold Arctic air to the north and mild mid-latitude air to the south. During this event, it is doing something else entirely. The jet stream has buckled. That's the technical adjacent way meteorologists describe what happens when the normally west to east flow develops extreme amplitude, meaning it swings dramatically north, then dramatically south, then north again, creating enormous waves in the upper atmosphere. Right now, 2 dominant features are locked into position over North America. A massive ridge, a northward bulge in the jet stream, is sitting over the western United States. And a pronounced trough, a deep southward plunge, is positioned over the eastern United States. These 2 features are the direct atmospheric cause of everything this storm is doing. The ridge is the heat dome. When the jet stream loops northward over the western states, it allows high pressure to build beneath it, suppressing cloud cover, trapping heat, and producing those record-breaking March temperatures in Phoenix and Los Angeles. Meanwhile, the trough over the eastern U.S. is doing the opposite. It's allowing Arctic air to plunge southward, far beyond its normal seasonal boundary, while simultaneously creating the low pressure zone where the storm is forming. The boundary between those 2 air masses, the warm tropical air being dragged north from the Gulf and the Arctic air pouring south behind the storm, is where all the atmospheric violence is concentrated. That boundary becomes dynamically unstable, which, in meteorology, is not just a figure of speech. It means the atmosphere is in a state where small perturbations get amplified. A little rotation becomes more rotation. A little lift becomes explosive lift. And moisture that enters that zone gets converted into precipitation at a rate that produces both record snowfall and severe thunderstorms, depending on which side of the boundary you happen to be standing on. Meteorologists sometimes call storms like this kitchen sink storms because they produce nearly every category of hazardous weather at once. You get the blizzard, you get the severe thunderstorms, you get the ice, you get the flooding, you get the damaging winds, and you get the heat dome sitting just far enough to the west to add a surreal backdrop to everything else. But the jet stream buckle is just the large-scale stage. The actual fuel delivery for this storm operates at a completely different altitude, and it's moving faster than most people realize. There are two jet streams involved in this storm, and most people only ever hear about one of them. The polar jet stream at 30 to 40,000 feet is the one in every weather forecast graphic, the broad ribbon of upper-level flow that steers storm systems across the country. But the feature that is arguably more important for the severe weather component of this event sits much lower in the atmosphere, around 5,000 feet above the surface, at what meteorologists call the 850 millibar pressure level. This is the low-level jet stream, and during this event, it is forecast to exceed 70 knots. That's roughly 80 miles per hour, at 5,000 feet, in the middle of the night. The low-level jet functions like a high-pressure hose pointed at the storm. It transports enormous quantities of warm, moist Gulf air northward into the developing convective zone at extraordinary speed. Dew points ahead of the squall line are forecast to reach the mid-60s in states like Tennessee and Kentucky, and could approach 70 degrees Fahrenheit in parts of the Carolinas. Dew points in the mid-60s in March in the mid-latitudes are genuinely anomalous. Those are moisture values more typical of late June. They indicate that the atmosphere ahead of the storm is holding a tremendous amount of water vapor, which is a direct measure of energy. When that vapor is lifted and condensed, it releases latent heat, which drives updrafts, which deepens convection, which strengthens the storm further. But moisture alone doesn't produce tornadoes. The other ingredient the low-level jet provides is wind shear, and this is where the setup becomes particularly favorable for rotation. Wind shear simply means a change in wind speed or direction with altitude. When the low-level jet is pumping warm air north at 70 knots at 5,000 feet, while the surface winds below are moving at a different speed and direction, and the upper-level jet stream above is flowing at a yet another angle and speed, the atmosphere develops what meteorologists call a strongly veering wind profile. This veering creates horizontal spin in the atmosphere, invisible tubes of rotating air lying parallel to the ground. When a thunderstorm's updraft tilts those tubes vertical, the entire storm begins to rotate. A rotating thunderstorm is called a supercell, and supercells are the specific storm structure most responsible for producing significant long-track tornadoes. The 70-knot low-level jet in this event is essentially preloading the atmosphere with both fuel and rotation before the storms even form. It's worth comparing this to past major severe weather outbreaks, where similar low-level jet configurations existed. Events where forecasters recognized the setup in advance, but still couldn't fully predict where the most violent tornadoes would touch down. That uncertainty isn't a failure of meteorology. It's a feature of the atmosphere's sensitivity to small-scale variations that no model fully captures. At the center of all of this, the jet stream, the moisture, the wind shear, is a pressure system that is rapidly becoming something remarkable. There is a term in meteorology that sounds almost violent because it is explosive cyclogenesis. Cyclogenesis simply means the formation or strengthening of a low-pressure system. It happens constantly across the planet, thousands of times per year, in varying degrees of intensity. But when a surface low-pressure system drops 24 millibars or more in pressure within a 24-hour period, meteorologists classify it as undergoing explosive cyclogenesis, sometimes informally called bombogenesis, or a weather bomb. The pressure in this system is forecast to fall below 990 millibars, and the rate of that descent matters enormously. Here's why pressure matters. Air flows from high pressure to low pressure, always, the way water flows downhill. The greater the difference in pressure between two regions, the steeper the pressure gradient, the faster the air accelerates to equalize it. That acceleration is wind. When a low-pressure center deepens rapidly, the pressure gradient around it steepens rapidly, and winds respond almost immediately. This is why storms that undergo explosive cyclogenesis can go from concerning to catastrophic in a matter of hours. catching forecasters and the public alike in a race against physics. This particular system is deepening as it moves toward the Great Lakes, drawing energy from multiple sources simultaneously. Latent heat released by condensing moisture in the convective systems ahead of it feeds energy back into the low. The jet stream overhead is enhancing the upper-level divergence above the low, which allows surface air to accelerate inward and upward more efficiently. The temperature contrast between the Arctic air mass to the northwest and the Gulf-sourced warm air to the southeast is providing the baroclinic energy, the stored thermal energy in contrasting air masses that mid-latitude cyclones feed on. Mid-latitude cyclones like this one are, in a sense, nature's heat redistribution mechanisms. They exist because the atmosphere is constantly trying to reduce the temperature difference between the equator and the poles, and the most efficient way to do that is to spin up low-pressure systems that mix warm and cold air together. This storm is doing exactly that, just with unusual intensity, because the temperature contrast fueling it is unusually large. Phoenix at 100 degrees and Wisconsin at 0 wind, chill, is not a normal March contrast. That is a contrast the atmosphere is going to try to resolve, and it's going to do so violently. Mid-latitude cyclones of this type are entirely normal meteorological phenomena. What is not normal is the magnitude of the forcing behind this one, but the most destructive part of this system may not be the low-pressure center itself. It may be what forms along its cold front, a single line of thunderstorms stretching hundreds of miles, moving through the dark. Picture a wall, not a storm cell, not a cluster of thunderstorms, not a swirling supercell on a radar screen. A wall, hundreds of miles long, moving northeast at 40 to 50 miles per hour, filled with lightning, hail, 60 to 75 mile per hour winds, and embedded rotation that can drop a tornado before radar even confirms it's there. That is what a squall line looks like, and that is what this storm is expected to produce. Quasi-linear convective systems, the technical name for squall lines, form along cold fronts when the temperature contrast between air masses forces rapid lifting along a linear boundary. As the cold front advances, it undercuts the warm, unstable air ahead of it, forcing that air sharply upward. That lifting triggers convection. The convection organizes into a line, and the line moves with the front. The result can be a structure that maintains its organization for 12 to 18 hours, crossing multiple states in a single overnight period. Within the squall line, the danger isn't always obvious from outside. The embedded rotation, small vortices that spin up inside the linear structure, are what produce QLCS tornadoes. And as mentioned earlier, those tornadoes are nearly invisible on radar until they are already on the ground. But beyond the tornado threat, squall lines also produce widespread wind damage that doesn't require a tornado at all. Bow echo formations, arc-shaped bends in the squall line where the wind is accelerating outward, can generate straight-line winds exceeding 75 miles per hour over a swath hundreds of miles wide. Trees come down, power lines fail, roofs lift, and it happens fast, in the dark, with almost no structural difference on radar between a 60 mile per hour wind event and one that touches 80. Arrival times for key cities in the squall line's path are being tracked carefully, and the overnight window, roughly 8 p.m. to 4 a.m. local time, is when the system traverses the most densely populated parts of the threat zone. The overnight danger, the same midnight tornado problem discussed earlier, applies not just to the tornado risk, but to the wind damage risk as well. 75 mile per hour winds at 2 in the morning with no warning and no power are a different emergency than the same winds at 2 in the afternoon. There is, however, a scenario that meteorologists are watching even more closely than the squall line. A scenario that, if it develops, could push this event from dangerous into something significantly more severe. Every major severe weather outbreak has a variable that forecasters acknowledge but cannot fully predict. And for this event, that variable is whether discrete supercells develop ahead of the squall line. Probability estimates for this scenario currently sit around 30 to 40%. It's not the most likely outcome, but it's not a long shot either. And the difference in impact between a squall line only event and an event that also features isolated supercells is substantial enough that it warrants serious attention. Supercells form when individual thunderstorms remain separated from the squall line, isolated enough that they don't get absorbed into the linear structure and lose their rotational organization. An isolated storm in a high shear, high instability environment can develop a persistent mesocyclone, a rotating updraft that drives all the other features of the supercell and creates the specific conditions under which the atmosphere generates significant tornadoes. Long-track tornadoes, the ones that stay on the ground for 30, 50, even 100 miles, come almost exclusively from supercells. The EF4 and EF5 events that reshape communities come from supercells. Whether supercells form in this event depends on subtleties in the atmosphere that even the best models don't resolve perfectly. The amount of capping, a layer of warm air in the mid-atmosphere that inhibits convection from firing prematurely, determines whether storms stay discrete or erupt all at once into a messy squall line. The timing of the cap's erosion, the exact placement of the warm sector boundary, the amount of cloud cover that either charges or suppresses surface heating. These factors shift by small amounts and produce radically different outcomes. A difference of a few degrees in a capping layer can be the difference between isolated supercells capable of producing violent tornadoes and a convective mess that produces widespread wind damage but limited tornado activity. Storm chasers and meteorologists will be watching their radar extremely carefully throughout Sunday and into Monday morning, looking for the signature of rotation that indicates a supercell has separated from the line. If that happens, the threat escalates significantly. If it doesn't, the squall line scenario is dangerous but more predictable. What makes this particularly hard to communicate to the public is that uncertainty in forecasting doesn't mean the threat is smaller. It sometimes means the threat is larger, because the atmosphere has more room to surprise you in the wrong direction. The worst tornado outbreaks in American history were preceded by forecasts that acknowledged exactly this kind of uncertainty. The forecasters were right to be uncertain. The storms were right to be worse. Yet even this powerful, complicated, dangerous storm raises a question that goes beyond the weekend forecast. Because this storm doesn't exist in isolation. It's a product of an atmosphere that has been behaving strangely for months. The Day 4 enhanced risk issued for the East Coast is the kind of forecast product that meteorologists don't file lightly. The Storm Prediction Center issues enhanced risk outlooks, the orange tier in their 5-level system, when the probability of organized severe weather is elevated and the potential for significant events is real. Issuing one 4 days in advance for a region like the Mid-Atlantic that doesn't commonly experience tornado outbreaks is notable enough that forecasters made a point of explaining it publicly. Only 3 comparable events have occurred in the past 11 years. That's not a common calibration. That's a signal that the atmospheric setup is genuinely unusual. The severe weather probability for parts of the Mid-Atlantic in this event sits around 30%. Washington, D.C., Raleigh, and Wilmington are all within the potential impact zone. East Coast tornado outbreaks are uncommon for a combination of reasons. The terrain is more varied than the flat plains. Surface heating is typically lower, and the warm sector of storm systems has usually lost some of its punch by the time it reaches the Appalachians and the Atlantic coastal plain. But this event bypasses some of those limiting factors because the moisture feeding it is exceptional. Dew points are forecast to reach the mid-60s in parts of Pennsylvania. In March, dew points in the mid-60s suggest moisture values more typical of a Gulf Coast summer event than a mid-spring mid-Atlantic setup. That moisture level, if it verifies, creates instability values comparable to classic tornado outbreak days in the southeast, in a region and at a time of year when forecasters and residents alike are not accustomed to taking those threats seriously. This is partly why the Day 4 issuance matters so much. It's a form of lead time that allows emergency managers, broadcasters, and individuals to prepare rather than react. And preparation for a tornado threat in the mid-Atlantic looks different than it does in Tornado Alley, because the infrastructure of storm awareness, the shelter culture, the weather radio habits, the community-level preparedness is generally less developed in states where severe weather outbreaks happen once every few years rather than every spring. Meanwhile, on the other side of the country, the western states are experiencing a completely different extreme that has been building for much longer than this single storm. The heat unfolding across the Southwest right now is not a weather event in isolation. It is a data point in a pattern, and the pattern is unusual enough that scientists have been tracking it all winter. Temperatures running 20 to 30 degrees above normal for March are what happen when multiple forcing mechanisms align at the same time. The jet stream ridge over the western states is part of the story, but it's not the whole story. This past winter was the warmest on record for several western states, continuing a trend that researchers have been documenting with increasing frequency. Winter, it turns out, is the fastest warming season in large portions of the continental United States. The cold season is shortening, the cold extremes are moderating, and the transition seasons, March and April especially, are increasingly seeing temperature excursions that wouldn't have been statistically possible under the atmospheric baseline of even 20 years ago. If Los Angeles reaches 100 degrees this weekend, it will break a record that survived 1879 through 2026. 147 years of California weather, and this March pattern might be the one that finally exceeds it. Phoenix potentially logging its earliest triple-digit day ever recorded is not just a weather curiosity. It's a benchmark being crossed earlier on the calendar than any benchmark before it. The heat dome is expected to persist for 2 weeks. That's not a weekend event. That's a sustained alteration of the regional energy balance that will have downstream consequences regardless of what happens with the storm in the east. And here's something that doesn't make it into most weather reports. The ocean is involved in this in ways that the atmospheric models are only beginning to fully capture. The ocean temperatures off the California coast are unusually warm right now, and that's feeding into the heat in ways that deserve their own explanation. The water off the California coast is not behaving like March water. Ocean surface temperatures in the region are running at levels typically associated with mid-June conditions, representing a marine heat wave, a sustained period where sea surface temperatures are significantly above normal for a given location and time of year. Marine heat waves don't just affect marine ecosystems, though their effects there are dramatic. They affect the atmosphere above them in ways that compound terrestrial heat events and make them harder to break. Normally, the ocean provides a moderating influence on coastal climates. Cool sea air flows onshore during afternoon hours, capping temperatures and providing relief. When the ocean is anomalously warm, that moderating mechanism weakens. The sea breeze carries warmer air. Nighttime cooling is suppressed because the ocean, which stores heat far more efficiently than land, continues releasing energy into the atmosphere after sunset. The result is that heat events along the California coast become more intense and longer lasting than they would be if the same atmospheric pattern occurred over normal ocean temperatures. Scientists are currently investigating whether the anomalously warm Pacific waters are connected to the early stages of a developing El Niño pattern. Some climate models are suggesting the possibility of a strong El Niño cycle for 2026 into 2027, and if that signal is real, the warm ocean temperatures currently observed off California could be an early indicator. Ocean-atmosphere feedback loops during El Niño events can amplify both heat and precipitation extremes across North America in ways that often take regional weather patterns out of their historical operating range. The biggest long-term impact of what's happening in the West may not be the heat itself, though. It may be what happens after the heat, because the heat is landing on a snowpack that is already in crisis. Snow in the mountains of the western United States does a job that most people east of the Rockies never think about. It stores water. The winter snowpack across the Sierra Nevada, the Cascades, the Rockies, and the ranges feeding the Colorado River Basin functions as a natural reservoir. It accumulates over the winter, then melts gradually through spring and early summer, feeding rivers, recharging aquifers, and supplying the water systems that support roughly 40 million people across the American West. When the snowpack is deep and the melt is slow, that water delivery is steady and manageable. When the snowpack is thin and the melt comes early and fast, the system receives a surge it can't fully capture, followed by a drought it can't compensate for. Western snowpack is currently running near record lows across large portions of the region. The warm winter that set temperature records across multiple western states didn't just deliver warmth, it delivered rain where snow should have fallen, and it accelerated the melting of what snow did accumulate. The heat dome, now pushing temperatures toward 100 degrees in March, is accelerating that melt further, weeks before the normal melt season even begins. The Colorado River Basin is under particular scrutiny. The river and its tributaries supply water to Arizona, Nevada, California, Utah, Colorado, New Mexico, Wyoming, and parts of Mexico. The reservoir system along the river, Lake Mead, Lake Powell, and the network that feeds them has been operating below historical norms for years. A low snowpack winter, followed by an early and intense heat event, is not a scenario that helps those reservoirs recover. Scientists are warning about the potential for a runoff crisis. Too much water moving through the system too quickly in early spring, followed by critically low flows later in summer, when demand is highest. Earlier snowmelt also means earlier dry conditions in the forests above the reservoir basins, extending the window of potential wildfire ignition by weeks. But there is one more consequence of this event that will unfold in the days immediately after the storm passes, and it affects every part of the country, not just the West. After the storm, the atmosphere will swing. The Arctic air mass that has been pulled south behind the cold front will push through the same regions that were experiencing severe thunderstorms and tornadoes Sunday night. Communities in Tennessee, Kentucky, Indiana, and Ohio that are under tornado warnings Sunday evening could be experiencing freezing temperatures Monday and Tuesday. The warm sector that made those storms possible, the balmy, humid, Gulf-sourced air that drove dew points to the mid-60s, will be replaced within 24 to 48 hours by air that originated over Arctic Canada. Meteorologists call this temperature whiplash, and it is increasingly one of the signature features of a transitional atmosphere operating at high amplitude. The temperature swings aren't just dramatic, they're rapid. A 50-degree temperature change in less than 2 days is not unusual in the immediate wake of a major cyclone passage, but the frequency with which those swings are occurring has increased. Plants that have begun to bud in response to the early warmth, and in much of the Mid-South and Mid-Atlantic, trees and crops have been responding to an unusually warm February and early March, will face the prospect of a killing frost days after tornado-producing warmth. The agricultural consequences of this kind of whiplash accumulate quietly, below the level of headline weather. Fruit crops, early vegetable plantings, and perennial plants that have broken dormancy ahead of schedule are extremely vulnerable to a sudden hard freeze after thermal priming. Power demand spikes during sudden cold events as heating systems respond to temperatures that drop far below what the infrastructure was expecting. Later in the week, the forecast models show warm air returning, and the cycle begins again. Warm, violent, cold, warm again, in the kind of rapid atmospheric oscillation that is increasingly difficult to plan around. Is this just weather, or is this a signal of something larger shifting in the atmospheric system? That question is worth sitting with. The atmosphere is not politically neutral territory right now, and I mean that in the scientific sense. There is an ongoing debate among climate scientists about a phenomenon called Arctic amplification, and this storm sits squarely inside it. The theory begins with a well-documented observation. The Arctic is warming roughly 2 to 4 times faster than the global average. This is not disputed. The mechanism, reduced sea ice, means less reflection of solar radiation, which means more warming, which means more sea ice loss, is well understood. What is not settled is what that accelerated Arctic warming does to the jet stream. Some researchers argue that as the Arctic warms faster than the mid-latitudes, the temperature gradient between the pole and the equator decreases. That gradient is one of the primary drivers of the jet stream's speed and stability. A weakened gradient could slow the jet stream and cause it to meander more, producing exactly the kind of amplified, wavy patterns that generate the large ridges and troughs we see in this event. Deeper troughs mean more intense cold outbreaks. More prominent ridges mean more intense heat domes. And the transitions between them become more extreme and more rapid. Other researchers are skeptical of this mechanism, arguing that the data doesn't yet support a clear causal link between Arctic warming and jet stream behavior at the level of individual extreme events. The science is genuinely unresolved. It is important not to overstate the conclusions, and I'm not going to do that. What I can say is that the pattern we're observing this week, an amplified jet stream, a massive western ridge, a deep eastern trough, simultaneous heat, and blizzard and tornado threat, is the kind of pattern that the Arctic amplification hypothesis predicts would become more common. Whether that pattern is actually becoming more common, and whether Arctic warming is the cause, is a question that researchers are actively working to answer with better data and better models. So here's where we land. 1 storm, 3 extremes, 1 weekend, up to 40 inches of snow across the upper Midwest, a tornado outbreak stretching from East Texas to the East Coast, a historic March heat dome approaching 100 degrees in the Southwest, temperature whiplash that will follow within days, over 100 million people inside the system's reach. The single most important thing I can tell you is about the timing. The overnight window, Sunday night into Monday morning, is when this event reaches its most dangerous phase. QLCS, tornadoes embedded in a fast-moving squall line, moving through Nashville and Louisville and Indianapolis and Cincinnati, while the people in those cities are asleep. 75-mile-per-hour winds arriving without the visual warning of a darkening sky, because there is no sky visible at 2 in the morning. Snow bands producing 3 inches per hour across the upper Midwest, filling roads while motorists attempt to reach safety. Weather awareness at night requires a different kind of preparation than weather awareness during the day. It requires charged devices. It requires alerts that are on and set to their maximum sensitivity. It requires knowing in advance what your shelter location is inside your home, because you may have less than 5 minutes to reach it. In the tornado threat zone specifically, the lowest level of your home, away from windows, in an interior room, not the second floor, not next to a glass door, the lowest interior point you can reach. The atmosphere is not new at this. Mid-latitude cyclones have been spinning over this continent for as long as there has been a continent. March storms have buried cities and spawned tornadoes and produced temperature swings that history recorded with a kind of wonder. What changes is our ability to understand what's happening and why, and with that understanding comes the ability to prepare rather than react. Understanding atmospheric patterns is the only way to anticipate future storms. The jet stream buckle that is driving this event is not mysterious. The low-level jet transporting Gulf moisture into the threat zone is not mysterious. The explosive cyclogenesis deepening the low over the Great Lakes is not mysterious. They are knowable. They are forecastable. And in the gap between forecasted and acted upon is where the difference between a close call and a disaster is usually made. The atmosphere is always changing. It has been changing since the first molecules of gas gathered around this young planet 4.5 billion years ago. It will be changing long after we are here to measure it. But sometimes, in the span of a single weekend, in the arc of a single storm, it reminds us, with complete impartiality and no malice whatsoever, exactly how small we are inside it, and exactly how much we owe to the science that lets us see it coming. Stay safe this weekend. The storm is already on its way,